Welcome to Jom Studyla YouTube channel. Today we are excited to share with you on chemical periodicity, an essential concept in understanding how elements behave and interact. We will explore patterns in periodic table trends, in properties like atomic size, ionization energy, and electronegativity, and how these trends help us make sense of chemical behavior across different elements. So, without further ado, let's dive into the fascinating world of chemical periodicity. Chemical periodicity on the effective nuclear charge and electron shielding. Effective nuclear charge, ZEFF, is the total positive charge and electron field from the nucleus. It is less than the actual nuclear charge because inner electron block shield some of the attractions from the nucleus. Formula: C effective equals to Z minus S. Z is total number of proton, so for nuclear charge, and S equal to number of inner core electron that shield outer electron. Example 1. Lithium, 3 lithium atoms. In terms of the electron configuration, 1s2, 2s1. Z equals to 3 proton, and S equals to 2 inner electron in 1s. And Z effective equals to 3 minus 2 equals to positive 1. Example 2. 13 aluminum atoms. Electron configuration is 1s2, 2s2, 2p6, 3s2, and 3p1. Z equals to 13 proton. S equals to 10 electron in 1s, 2s, and 2p shells. And Z effective equals to 13 minus 10 equals to positive 3. Shielding effect. The shielding effect is related to the number of electron shell in an atom. It happens because electrons repel each other like charges repel. Inner electron closer to the nucleus blocks some of the attractions between the nucleus and the outer electrons. This makes it easier to remove outer electrons because they feel less pull from the nucleus. Electrons in the same shell, same energy level, also repel each other, but not as effectively as inner shell electron. So, inner electron shield better than electron in the same subshells or energy level. Below is the diagram. Shielding effect happens when electron block or reduce the pull of the nucleus on the other electron. Inner electron block the outer electron better than electron in the same shell or orbital. Atom radius. By definition, the atom radius is the estimated size of an atom calculated as half the distance between two bonded atoms of the same element. Formula: atom radius is D equals to A divided by 2, where A is the distance between two bonded atoms. Atomic radius trend in the periodic table. Across the period left to the right, trend is where atomic radius decreases. The reason, as you move across a period, the number of protons increases, leading to a stronger attractions between the nucleus and electron. These pull electron closer, which is reducing the atomic size. Example, comparing sodium and chlorine. Sodium, the atomic number is 11, and atomic radius is 186 picometer. Chlorine, atomic number is 17 and atomic radius is 99 picometer. Despite both having similar electron configuration, chlorine higher nuclear charge pull its electron closer, resulting in a smaller atomic radius. Atomic radius trend in the periodic table, down a group from top to bottom, the trend is atomic radius increases. Reason, each step down a group add a new electron shell, increasing the distance between the nucleus and the outermost electron. This leads to a larger atomic. Example, comparing lithium and cesium. Lithium and cesium. Lithium atomic number is 3 and cesium atomic number is, lithium's atomic radius is 152 and cesium atomic number is 55 and atomic radius is 265 picometer. Despite both being alkaline metals, cesium has more electron shell than lithium, resulting in a larger atomic radius. Effective nuclear charge, electronic configuration, and atom as per the table. So we have here is 11 sodium atom. The electric configuration is 3s1 and the Z effective is +1. And atomic radius for sodium is 186. And magnesium, we have 12 magnesium atom. The electronic configuration is Ts2, 3s2, and the Z effective is +2, and the atomic radius for magnesium is 160 picometer. For 13 aluminum atoms, the electronic configuration is 3s2, 3p1, and the Z effective is +3, and the atomic radius is 143 picometer. And for the silicon, 14 silicon atoms, the electronic configuration is 3s2, 3p2, and the Z effective is +4, and the atomic radius is 117 picometer. And for the phosphorus, 15 phosphorus atoms, the electronic configuration is 3s2 and 3p3, and the Z effective is +5, and the atomic radius for 15 phosphorus atom is 110 picometer. And then we have sulfur, 16 sulfur atom. The electronic configuration is 3s2, 3p4, and the Z effective is +6, and atomic radius is 103 picometer. And finally, we have 17 chlorine atom. The electronic configuration is 3s2, 3p5, and the Z effective is +7, and the atomic radius is 99 picometer. Ionic radius. We have cations, which is positive ion, and we have anion, negative ions. Cations are always smaller than their original atom. This is because they lose one or more electron from the outer shell. When this happens, the atom becomes smaller. Across a period left to the right, cation gets smaller, and this happens because the effective nuclear charge, Z effective, increases, pulling electron closer to the nucleus. Down a group, top to bottom, cation get larger because more electron shells are added. On the other hand, anions are always larger than their original atom, and this is because they gain one or more electrons. And the extra electron cause more repulsions between them, so the outer shells spread out. Across a period, anion gets smaller as the nuclear charge increases, pulling electrons in more tightly. This is a relative ionic value of atom and ions in picometer. We have the alkali metal, and you have the alkaline earth metal, which is in a group 2. And we have aluminium in a group 13. And carbogen and halogen is to form -2 and -1 ions. So you can observe from this table for the relative ionic value of atoms and ions. And for this table, note that ionic value of ions are larger than atomic value due to electronic gain and increased repulsions. Ionic radius of ion with isoelectronic configuration. So we have sodium, magnesium, aluminium, and we have and etc. So as you go down a group in the periodic table, negatively charged ions get bigger because they have more electron shells. So some atoms and ions like sodium, magnesium, aluminium, oxygens, and fluorine, and have the same number of electrons. And these are called isoelectronic because they have the same electron configuration. Even though they have the same number of electrons, their sizes are different. The more positive the charge, greater nuclear charge, the smaller the ion. For transition elements, the ionic size also decreases as you go across the period, but this decrease is not very large. That's all for today's presentation. That concludes today's session, and I look forward to seeing you at the next session. And please subscribe to German Study Lab YouTube channel. And don't forget to turn on your notifications so you don't miss any update. Best of luck in your studies and upcoming exam. Wishing you all the best. Thank you very much for your support and cooperation.